Hello there, calculus fans. Welcome back. We have a couple of free response questions that address some common issues that we're faced with during the AP test. For instance, problem number 1, part B. F of x is defined, an algebraic function, and we are asked to write an equation for the tangent line to the graph of f at x equals 2. Of course, you know that in order to find the equation of a tangent line to a function, we need to have an x and y coordinate that's common to both points or both functions, x, y. And we also need to know what is, if this is f of x, then we need to find f prime of x. And of course, that would be equal to the slope of our tangent line. So you want to file these topics away under these broad general, umbrellas. And that way you can make these connections quickly. So here, I think the first thing I would like to do is to find out what is f of 2. So I have a y coordinate to go along with that x coordinate. So we have 4 times 2 cubed, that's 8. So 4 times 8 minus 6 minus 1. So I have 32 minus 7. So it appears that the y coordinate is 25. That gives us an ordered pair of 2 and 25. We're still missing the slope of the tangent line, but that would be, of course, represented by f prime of x. So we'll take our derivative, and so we have 12 times x squared minus 3. We do need to evaluate this, so f prime of 2 is given to us as, let's see, 12 times 4 minus 3. So we have 48 minus 3, that's 45. And so the only thing I think we omitted was, of course, the point slope formula from Algebra 1, y minus y sub 1 equals m times x minus x sub 1. Of course, now our slope is represented by f prime of 2. So the final answer, y minus the y coordinate at that point, the point of tangency, and of course the f prime of 2, which is 45, and we have x minus 2. So we have the final answer right here. Okay? Common question. We need to make sure that we understand what the necessary conditions are. And of course, there it is. Our next question. We have a piecewise defined function. Both definitions are continuous everywhere. One is linear, one is quadratic. The partition changes place at x equals 2, and that's where the definition switches from one to the other. Part A, we are responsible for, let's see, what value of k will f be continuous at x equals 2? The justify your answer requires that we use proper mathematical notation and communicate clearly. So the definition at a point for a function in calculus requires that we identify the value of the function. F of 2 is equal to 2 times 2 plus 1, and hence we have 5. We also need to find the right-hand limit, so limit as x approaches 2 from the right for 2x plus 1 is equal to 5. We also need the right-hand limit. And again, we need to show the work just about exactly the way I'm showing here. Let's see, 1/2 x squared plus k. And let's see, this ends up being, let's see, 4, okay, 2 plus k. Now, for the function to be continuous at x equals 2, all 3 of these expressions must equal each other. So 2 plus k is equal, that's a bad looking k, but there it is, it's a little better. So 2 plus k is equal to 5, and so now we need to subtract 2, and let's see what we get. We'll teleport up there, and so we end up with k is equal to 3. So now we have established, we have justified by showing all of our steps using appropriate limit notation, evaluating the left-hand limit, right-hand limit, as well as the value of the function. All 3 must be combined, and this yields k equals 3. So under that condition, f of x will be continuous at x equals 2. Part B builds on this. Use the value of k found in Part A to determine if f is differentiable at x equals 2. Use the definition of the derivative to justify your answer. Okay, so we have, let's see, f of x is equal to, so there's no change here, 2x plus 1, but here 1/2 x squared plus 3. This is our new function f of x, and this is still at x is less than or equal to 2, and this is x greater than 2. Okay, so they're asking us to use the definition of the derivative. That means that we are going to look at the following. Uh, let's see, the limit. Now remember, this is the numerical derivative at a point, namely x equals 2. So we're looking at the limit as x approaches 2 from the left. And we have, let's see, 2x plus 1 minus the value of the function at that point. And I think we determined that that was 5 over, let's see, x minus 2. Okay, and if you're saying, okay, I'm a little fuzzy about this limit definition that you're using, our textbooks identifies that as the alternative form of the definition of the derivative. So f prime of a, so if a is the value of x where we're trying to find the derivative, then this would be equal to the limit as x approaches a for f of x minus f of a over x minus a. Now, you don't get credit for writing recipes like this on the AP test. You get credit for what I have written on the left side here underneath Part B, but I just want to communicate with you as to where this formula is coming from so that way you're embracing that and saying, aha, I got you. And so let's see what we have here. This, of course, simplifies to the limit as x approaches 2 from the left, and then we have 2x minus 4, all that over x minus 2. And I see you smiling already. You're saying, okay, so what we're going to do is simply factor out a 2, which gives you an x minus 2 on top, and the x minus 2 that's causing us grief in the denominator, because if we plug in directly to evaluate the limit, we would get 0 over 0. And of course, this the x minus 2's cancel out, and we have the limit as x approaches 2 from the right, left, that is, for 2, and the limit of a constant is the constant itself. Good. Well, we did half the work that's necessary. We also need to, of course, find and check out the limit as x approaches 2 from the right for this function. And that, of course, the definition changes to 1/2 x squared plus 3. And let's see, we have, that's the f of x portion. Then we have to find the f of a. And so when we plug in the x equals 2 to evaluate f of a, what do we get? We end up with 4, well, that's 2. We get 5. And in the denominator, we have, of course, x minus 2. Well, let's see where this takes us. We end up with 1/2 x squared minus 2, all that over x minus 2. And of course, we're finding the limit as x approaches 2 from the right. And yes, we have a problem. We have 0 over 0. And so we need to do a little bit of mathematical magic. I think that the best way to do this is to simply get rid of that fraction that's in front of the x squared by multiplying by 2 over 2. And so when we do that, let's see what we get. Limit as x approaches 2 from the right for, let's see, x squared minus 4, all that over. And in the denominator, I'm hoping to cancel out the factor of x minus 2. So instead of distributing the factor of 2 that we just introduced, I will just indicate that we are multiplying by 2. And this gives us an opportunity, I know that you already see this, to factor the numerator. And as it turns out, we're very fortunate that you have x minus 2 as a factor, and that's crucial to our well-being because we really need x minus 2 to cancel in order to evaluate this limit at x equals 2 to find that the function f of x is differentiable there. So what do we get? Limit as x approaches 2 from the right. I believe we end up with a remaining function of x plus 2 over 2 once we've canceled out our factors of x minus 2. And this gives you a 4 over 2 and 2. And because we have the limit here equaling the limit here, consequently, we have established differentiability of f of x when k is equal to 3. Okay? And this was the required work. You see, justify your answer. So we have that. Now, I have not explicitly stated, okay, that the function f is differentiable at x equals 2. So I must do that so that that way whoever is scoring my response, of course, says, ah, they understood what this means. So let me go ahead and indicate, therefore, f of x is differentiable at x equals 2. Bang. Okay? So again, lots of work required. We needed to make sure that we complied with using the definition of the derivative. We did. We had choices, but because we were finding the numerical value of the derivative at x equals 2, I think that the quickest and easiest way to do this was to go ahead and use the alternative form, or better known as the numerical value of the derivative at a point. Okay? So moving on, this is again a very popular type of question. So again, I think we have a twist on what we just did in problem number 4. Let f be the function defined as follows. Okay, and so f of x is displayed for x less than 1, and of course for x greater than or equal to 1. And we are told that a and b are constants. Again, we need to make note of the partition that happens at x equals 1. So the definition of f of x changes at that location. So describe all values of a and b for which f of x is continuous function. And again, remember, we need those 3 conditions. And so let's go ahead and identify f of 1. And so at this point, the f of 1 would be a times 1 squared plus b times 1. So we have a plus b as the value of f of 1. Okay, moving on. The limit as x approaches 1 from the left, and we have, let's take a look at this, the absolute value of x minus 1 plus 2. Okay. And this, often these absolute values create a problem for us. Not here. We can evaluate by direct substitution, and we simply end up with 2. Okay. The limit as x approaches 1 from the right, we end up with, let's see, well, our function is ax squared plus bx. So when we find this limit, we have a plus b. We've seen that before. And of course, the 3 expressions equal each other. So a plus b is equal to 2. Now, we don't have a equals a number or b equals a number, but we have basically a plus b equals 2. And this would need to be a condition for f to be continuous. And the instructions were describe all values of a and b for which f is continuous function. We just did. A plus b must equal 2. You could write it as b equals 2 minus a, or a equals 2 minus b. I think we're happy, and we're going to leave our answer as is. Okay? That's the description. We have a clear relationship between a and b. Now, moving down, for what values of a and b is f both continuous and differentiable? So we already have the requirement for continuity, a plus b must equal 2. Now we're going to, of course, look at differentiability, and there are no restrictions here in terms of how I can show my work. So instead of using the limit definition of the derivative, what I'm going to do is I'm going to find the derivative for f of x as described here, and then find the limits of those derivatives. But I need to do a little bit of legwork here, okay? Remember, I told you we dodged a bullet about the absolute value of x minus 1. Here, I think I need to go ahead and actually simplify that, because I need to take the derivative, and I can't do that at exactly 1, okay? Because we have a sharp corner there, so the derivative would not exist. But let's take a look at what I can do. Absolute value of x, as you well know, minus absolute value of x minus 1, that is equal to, as a piecewise defined definition, the opposite of x minus 1 when x is less than 1, and basically x minus 1 when x is greater than or equal to 1. So I will be compelled to use this portion right here, because when I'm taking the derivative for values of f that are less than 1, x is less than 1, that is, in that case, the definition is right here, okay? And that translates into the following. So let's rewrite f of x without the absolute value. And so we have f of x is equal to, well, negative x plus 1. I distributed the negative sign here in this expression, and plus 2, okay? And that's for x is less than 1. And we have, let's see, we don't need to do any mathematical magic on this other side. So there we are. And again, the only reason I needed to go ahead and simplify this expression, in fact, let me simplify it further to simply negative x plus 3, that's when x is less than 1, is because I can't take the derivative with the absolute value there. So let's take the derivative of this piecewise defined function, and we have negative 1 as the derivative when x is less than 1. And I'm using the shortcut techniques as we know it now. And we have, of course, let's see, 2ax plus b when x is greater than 1. I'm not including equal to 1 because I don't know if the derivative exists. So what we're going to do is find the limits, the limit as x approaches 1 from the left for f prime of x, which of course is a constant, and I end up with negative 1 because the limit of a constant is the constant. I will also check the limit as x approaches 1 from the right, and what do we get there? Well, let's see, we have 2 times ax plus b, and I end up with 2a plus b. And remember, in order for the derivative to exist here, we have to have a function that's continuous, but we've already established in part, I believe that was part B. Yep, in part B, that would be, the function would be continuous if a plus b equals 2. Now, on top of that condition, we must also have the limit of f prime of x as x approaches 1 from the left equal the limit of f prime of x as x approaches 1 from the right. And that would, of course, require that 2a plus b equal negative 1. So now we have 2 conditions that must exist for f to be differentiable at x equals 1. And in order to investigate this, we need to solve this system of linear equations in terms of a and b. And we can do that, of course. In fact, what I'm going to do is go up on top and solve for b in terms of a. So b is equal to 2 minus a. And the purpose of doing this is so that way I can now come down here, and I'm going to replace b with what b is equal to in terms of a, which is 2 minus a. And then this is, of course, an easy equation for us to solve. And so let's see what we get. I believe we have a plus 2 is equal to -1. And so a is equal to -3. Okay, and of course this is a simple system of linear equations. Probably we can go back up and say, all right, why don't we use b is equal to 2 minus a? And now that we have the value of a, we have, let's see, 2 minus -3. So b is equal to 5. We have the conditions for this function f to be continuous and of course differentiable, which is a prerequisite to differentiability at x equals 1. So for what values of a and b? Well, now we have specific values of a and b, which is phenomenal because that is what was asked for. And we have the supporting work, which is of course, let's take a look at it. It does not indicate here, okay, but we need to show our work, and indeed, just as we have with the appropriate limit notations, and of course an explicit and correct representation of our f prime function. And this concludes our journey. I believe this was the last question from the free response pool. So there you go. Again, notation, and clear communication is our focus. Until next time,